Section 1.5, infinite limits. So an infinite limit is a limit where the function increases or decreases without bound as x approaches some number c. So for example, if we look at the rational function, and we're trying to look at the limit as x approaches 0 from the right-hand side of 1 over x, it's infinity because notice that it's going to keep going up and up and up and up and up. It's never going to reach a specific value. It goes toward infinity. Same thing as we go from the left side. Now it's going to keep going down, 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 down. So that means our limit is negative infinity. Technically, since the limit is unbounded, it does not exist. But instead of writing dne like we have been, we can write infinity or negative infinity. So, first example, the limit as x approaches 1 of 1 over x minus 1 squared. So I have it graphed here in purple. The asymptote is at 1. And notice from both sides, it's approaching the same thing. It's going up forever and ever. So this limit is infinite, so it goes to positive infinity. The second one, I have it graphed over here in blue. So the limit as x approaches 4 of 3 over x minus 4. The asymptote is at x equals 4. Since they do not approach the same thing, technically it doesn't exist. But let's look at it piece by piece. Let's look at the left limit. Ooh, I can't write today. So the left limit, we're going down, 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 down. So we go to negative infinity. On the right, we keep going up. So the limit is going to be positive infinity. So review of pre-calc. A vertical asymptote is a vertical boundary line that the function never crosses. And remember, to find that, we set the bottom or the denominator of a rational function equal to 0, and then we solve to find the x values that have asymptotes. So finding the vertical asymptote for each graph. The first one, we want to set 2 times x plus 1 equal to 0. All right, so divide by 2, divide by 2. So x plus 1 equals 0 still, minus 1, minus 1. So we have an asymptote at x equals negative 1. Same idea for the second one. One thing you might want to consider first is to try factoring. So when we have that x squared plus 1 over x squared minus 1, notice that x squared plus 1 doesn't factor, so nothing on the bottom is going to be able to cancel out. So let's just solve it like we just did. X squared minus 1 equals 0. Add 1, add 1. X squared equals 1. Take the square root. So that means x is equal to plus or minus 1. So this one has 2 asymptotes, one at positive 1 and one at negative 1. All right. F of x equals cotangent of x. Remember, cotangent, okay, that's like 1 over tangent. Tangent is sine over cosine, so this is cosine over sine. So we want to know where is sine of x equal to 0. We can use our unit circle for that. And sine is 0 at 0, pi, 2 pi, and going on and on and on. So this has asymptotes every pi. So we can write that as x equals k pi. But remember, k has to be an integer. Really bad way of writing that. Okay. And the last one, another rational function. So let's try factoring first and see what we get. So the top should factor to x plus 4, x minus 2. And the bottom goes to x plus 2, x minus 2. Notice that these will cancel out. This is telling us we have a removable discontinuity at x equals 2. So to solve for an asymptote, set what's left, x plus 2 equal to 0, subtract 2, and we get an asymptote at x equals -2.